All right, so for question number 2, we're looking at these scientists and their invention, or the type of energy the inventor was able to produce and how it was produced. Okay, so let's start with Ørsted. What did Ørsted discover?
He discovered that there's a relationship between electrical and magnetic energy.
Right. Okay. He discovered there's a connection between electrical and magnetic energy. That connection being that an electric current can produce magnetic effects, okay, or a magnetic field around a current carrying wire. All right. What does that kind of led to? Well, that's how radio transmitters work. Okay. They produce magnetic fields, okay, that can be transmitted, right, and then received. All right. What about Faraday? Okay. Well, Faraday was looking at pretty much the same thing, except in the reverse. Yeah, he discovered that magnets can push electrons around, and that means that you can use a magnetic field to move electrons and generate a current or electricity. What about Seebeck? This had something to do with electricity as well, but it was something else, some other form of energy. Sure.
So that heat could be converted into energy.
Right. He found that heat could be converted directly into electricity, okay? Or rather, thermal energy could be converted directly into electrical energy by the use of a thermal-electric converter or thermocouple. Okay. What about Edison? Everybody should know Edison. He invented the light bulb. Okay. He found that electrical energy could be converted to heat and thus light. Okay. If you had the right metals, they would glow really, really hot and produce a lot of light as well as a lot of heat. Okay. And what about Volta? He made the first what? First battery. Okay. First battery converted chemical energy into electrical energy. Okay. For each of the inventions identified in question number 2, state a practical use for the invention today. Okay, well, we said that radio transmitters for Ørsted, Faraday a generator, Seebeck, okay, circuit breakers or thermocouples in brakes that can convert heat into electricity and charge the batteries of an electric car. Okay, Edison, well, we don't use incandescent light bulbs very much anymore. They're not very efficient, but I mean, they still serve the same purpose they used to. And obviously batteries also still serve the same purpose they used to. They power mobile devices. Okay. For number 4, what's the difference between nuclear fusion and nuclear fission? Okay, well, one does what to an atom, the other does the opposite. One breaks it, one forces them together, right? Okay, what's similar between the two is they both involve the energy that holds an atom together. Okay, either way you slice it or compress it, whichever, okay, the energy that holds the atom together is what gets released in either one of those processes. That's what they have in common. All right, modern theory of the source of energy for the sun is, of course, nuclear hydrogen fusion. Okay, for number 9, what did these people, what were their contributions? What did Sadi Carnot discover? It was right before Joule. He discovered...
Was it thermodynamics?
Yeah, sort of some thermodynamics, that thermal energy could be converted into mechanical energy. He paved the way for the internal combustion engine. Okay, expanding gases due to thermal energy could be used to do work. That's mechanical energy. Okay, what about James Young?
I think he was the guy who found like mechanical energy into thermal energy.
That was Black. Or actually, sorry, that was Rumford that did that. He was the Cannon guy. That was mechanical energy into thermal energy. Okay, go back here. So Black was the flow of energy. He was the thermodynamics guy, Joseph Black. And he was the hot to cold guy. Okay, and one more back here. There we go. Thomas Young, here we go. Okay, kinetic and potential energy in moving objects. Okay, I always get him and that other one mixed up. Okay, so kinetic and potential energy in moving objects. Essentially, he's the one who came up with this idea that energy is the ability to do work, its connection to mechanical energy. All right. Okay. Explain how Joule proved heat could be produced from potential energy. All right, so Joule had that falling block experiment, right? Okay, he said that potential energy is a form of energy. I can prove it by turning it into heat, okay, or turning it into thermal energy. Okay, the two blocks slam together, okay, and when they slam together, okay, the potential energy that the block had has been converted into mechanical kinetic energy. Okay, they smack into each other. That kinetic energy transforms into thermal energy, sound, okay, things like that. Right, and so that's how he proved that. Okay. For number 12, given the following situations, identify the major form of energy involved. Okay, an antacid tablet is placed in a glass of water and the tablet starts to bubble. Plop, plop, fizz, fizz.
Chemical?
That is chemical energy. Okay, it's a chemical reaction. Right? What's in an antacid tablet is basically a base. Okay, so when you put it in water, it bubbles and fizzes, and then when you drink it, it neutralizes the acid in your stomach and mostly your esophagus. That's what gives you heartburn. Okay. B, a fluorescent dial on a wristwatch glows at night. If it's glowing, it's
Light, but it can also be chemical because it's fluorescent.
yeah, it could be both, but I'd say the dominant one here would be light. Okay, we're looking at something that's emitting light, okay, so it's light energy. Downhill skier begins to ski down the slope with increasing speed. Mechanical energy. Okay, specifically, we're converting potential into kinetic. Yeah. All right, tingling sensation is felt on the tongue when it is touched to the terminals of a 9-volt battery. Anybody ever done that? Don't do it on anything bigger than a 9-volt battery. Okay, and it's not usually like tingling. It's usually a little bit of a zap if it's a good battery. Okay, there are far better ways to test a battery than that, but that's how we used to do it. Okay, we didn't have fancy batteries and testers and stuff like that. We just go, oh, that one's good. Yeah, good. Okay. This is the same kind of person, same kind of mentality of taking 2 wrenches and going, I wonder if this car battery is still okay. Okay. Don't do it. Okay. 12 volts, it's a lot. Okay, it's a lot. I accidentally went across the positive and negative posts on our circuit panel on our trailer when I was winterizing it last year, and I couldn't feel my arm for like 10 minutes. It was like ah! And it was not fun. Batteries were good though, okay? They were all good. Okay? Yeah, so watch out for that one. Don't want to play around with electricity. The inside of a car gets extremely warm if the car is left in the sunshine. Yeah, thermal energy, I'd also say maybe you could argue solar. I mean, it's the solar energy going through the window and then not being able to escape, that greenhouse effect kind of thing. Okay. A seagull lifts a clam high above the beach. Potential energy, we could also say mechanical energy because potential is part of mechanical. Okay. And then a compass needle is held over the surface of the earth and points north. Magnetic. Yeah. Okay. Describe an appliance or machine that for its operation requires the following forms of energy. Okay, what's something that requires chemical energy?
Battery.
Okay, it could be a battery. Okay. We do, yeah. Cars, lawnmower. Okay, any of those things would require that. Okay, what about light? A solar panel, yeah. Okay, if you have a solar powered calculator or something like that. Heat. What's that?
An old light bulb.
An old light bulb? Okay, it wouldn't necessarily require heat, though it would produce it. We need something that requires heat for its operation.
The piston in a combustion engine.
Yep. Okay, the heat from the exploding gases is what makes your engine go. It requires thermal energy. Okay, we could also say that might be chemical energy to start with, but yeah, it becomes heat for sure. It becomes thermal energy. Okay. Electrical. Anything you can plug into the wall or put a battery in that will work. Okay, that's a lot of things. Magnetic. Compass. Okay, wireless charger. Okay, that's going to use magnetic energy to charge your phone. Okay, number 14. Describe an appliance or machine that produces the following forms of energy as it operates. Okay, chemical. It may not be a machine, but I always say plants. Okay, photosynthesis produces chemical energy. Right? So that may not be a device or an appliance, but it's certainly something that makes chemical energy.
So any form of cellular respiration?
No, any form of cellular respiration is using chemical energy. It's burning the sugar, right? It's taking the chemical energy and turning it into something else. Okay? This has to be something that is going to produce that type of energy. Okay? And the only thing I could ever think of was a plant, and someone else said like an oil refinery. I'm like, okay, yeah, if you're refining oil, you are producing another form of chemical energy. You started with chemical energy, but you are producing another form of it. So, okay. Light. How about a light? That one's pretty easy. Okay. Thermal energy. A heater, yeah. Okay. Electrical energy. What's that? An outlet, generator, okay, solar panel is going to produce it, okay, stuff like that. And then magnetic, electromagnet, yeah, something like that, producing magnetic energy. All right, any questions on those? Okay. So we are going to look now at the laws of thermodynamics. Okay, so this is lesson 2 in your notes package. Okay, we're going to be looking at the laws of thermodynamics. So this is just so we understand, thermodynamics, what does that mean? Yes, exactly. Dynamic means changing, thermo means heat. Okay, so this is the changing or movement of thermal energy. Right? So the laws of thermodynamics govern the behavior, movement, transfer, conversion, etc. of all types of thermal energy. Okay, so all machines in daily life are governed by physical laws. Okay, these laws describe the relationships between work and mechanical energy transformations, or any energy transformations for that matter. Okay, so what we're going to look at here is first some terminology. Okay, and one of the most important terms we need to know, and when we're talking about energy, is the term system. Okay, a system is a series of interconnected parts. If you're looking at the strict definition of system. Okay? From an energy perspective, a system is a bunch of things that are essentially reliant on each other for the transfer of energy. Okay? So it's being transferred from one object to another. So if I'm standing here and I'm getting ready to push the chair, me and the chair are a system. Okay? Because I'm about to transfer energy to the chair when I push it. Okay? That would be a system. If you have a crane that's lifting a load to the top of a building, that's a system. The crane and the load and the cable between them are all allowing energy to be transferred from one part of the system to another. Okay, does that sort of make sense? Okay. Now, so a system, it says here, okay, is a set of interconnected parts. Right, and we talked about that already. Okay, there are 3 types of systems, and you should know what they are. Okay. The system types are based on whether matter and or energy can get in or out. Okay? So the simplest and most common type of system is an open system. Okay? And the definition of an open system is one that exchanges matter and energy with its surroundings. All right, let's see how that goes. All right, so open system, one that exchanges both matter and energy. It's even worse. Okay, so open system is one that exchanges both matter and energy with its surroundings. Okay, so that means that both things get in or out. So for example, if I'm mowing my lawn, okay, that's an open system. The lawnmower is pulling in oxygen, using it to burn the fuel, okay, putting off carbon dioxide, as well as heat. Okay, so both matter, okay, that would be the carbon dioxide and the oxygen, are being exchanged, but also energy is being exchanged. In the process of burning the fuel, heat is being produced, and the heat is going from the lawnmower to the surroundings. That's an open system. Okay? Basically, everything is exchanged. Okay? You and I, we're open systems. Okay? We're doing exactly the same things as the lawnmower. We're bringing in oxygen, we're putting off carbon dioxide. Heat energy can go in and out. All right? Most of the time, the heat energy flows from us to the surroundings because very rarely is it higher than 37 degrees around here. Okay? That kind of makes sense to everybody? Right? In fact, most of the time, I use this idea that you and I are open systems to heat this classroom. Okay? The thermostat in this classroom sucks. You can't control anything. It's either on or off. So the heat is like full blast or not on at all. Okay? So what I do is I just leave it off. Okay? Unless it's like 30 below, it works well enough, okay, that people come in here and they're warm, and they're warmer than the surroundings, and they'll warm the room. They'll keep it, okay, around the right temperature. I come in here in the morning and yep, it's going to be a little cool. It's going to be like 18 degrees, 17 degrees in here. By the end of the day, it's 22. Okay? Works great in the winter. Summer, not so good. No air conditioning. Okay? In June, come in here in the morning, it's like 21 degrees. By the afternoon, it's like 27. Okay? It's like sweat box in here by the afternoon. Okay? And that's because you guys put off so much thermal energy. And you're an open system. All right, closed system. Okay? A closed system is one that cannot exchange matter. Okay? So matter can't be exchanged, but energy can be. All right? So a closed system is airtight. Airtight, but not insulated. Okay? So energy can still be exchanged, but nothing material-wise gets in or out. So you go to the grocery store, they got a sale on chicken. You buy a whole bunch of it. Okay? You take it home, you put it in a Ziploc bag. Is it sealed airtight? Yeah, no matter is getting in or out of that Ziploc bag. You throw the Ziploc bag in the freezer, what's going to happen after a few hours? It's going to be frozen. Didn't exchange any material, but energy was lost. Okay? The chicken went from being not frozen to being frozen. Okay? And so as a result, it lost energy to the surroundings. But there's still the same amount of chicken. Okay? And there's still the same amount of gases in the bag and all of that kind of stuff. None of that was exchanged. It was sealed airtight, no matter got in or out. Okay? So anything that is sealed airtight and cannot exchange material with its surroundings would be considered a closed system. Okay? Probably the best closed system would be the International Space Station. Okay? It is a closed system. No material can get in or out with the surroundings. If it does, everybody on board dies. Okay? And that would be bad. Okay? Now, that said, every once in a while, they do have to make a poop comet, okay? Which is when they jettison the space toilet's tank. And every once in a while, you can see a shooting star. But it's the poop from the International Space Station. Yeah. All right, and of course they have to have material brought to them. Okay, they're not completely self-sufficient. So, okay, that's things are being brought back and forth. Right, but they do have energy exchange with the vacuum of space. Okay, energy is lost, energy is gained depending on whether they're in the sun or in the dark. They use solar panels to gain energy from the sun, so that's a closed system. Okay. An isolated system is essentially theoretical. Okay? It is not possible to perfectly isolate anything, energy-wise, from its surroundings, but we can get fairly close. Okay? So an isolated system does not exchange either matter or energy with its surroundings. Okay? So if something was perfectly isolated, its temperature would remain the same, no energy would be lost or gained, and no matter would be exchanged either. Okay? Everybody all right with that? Okay, so the first law of thermodynamics is really just, I don't know why it says and the law of conservation of energy. It should say is the law of conservation of energy. Okay? Which works just the same as the law of conservation of matter. It just says energy cannot be created and it cannot be destroyed. Okay? That is the first law of thermodynamics. Okay? Energy can be gained, it can be lost, it can be converted, right? It can be used to do work. all of that stuff, but it cannot be created or destroyed. Energy cannot come from nowhere. Okay? Everybody all right with that? All right, so important to distinguish heat from work. That is important. We have to understand the difference. Okay, but first let's look at the similarities. Heat is a transfer of what kind of energy? Thermal. Work is a transfer of mechanical. So they're both transfers of energy. What's different is what energy they transfer. Okay, so if it's heat, it's a transfer of thermal energy. So when you put something in the microwave, you're heating it up because you're transferring thermal energy from the microwave to whatever is in it. Okay, putting something in the microwave doesn't do work. Actually, it does. Why? Right, it spins around and around. Okay, inside the microwave, work is also being done. The mechanical energy of the object is changing because it's being spun around and around. Okay. All right, so the energy of a system, okay, can be increased in two ways. You could heat it, that is transfer thermal energy to it, or you could do work on it or to it. Okay? Either one of those will result in a change in energy, either mechanical or thermal. Everybody okay with that? The opposite is also true. The system could heat something else, that is transfer thermal energy to a less energetic object, or it could do work on something else. If it does that, it's going to lose mechanical energy by transferring it to the other object. Okay? So energy can be increased or decreased in those two ways, either by heat or by work. Everybody okay with that idea? Okay? That's what the law of conservation of energy is saying. You can't create it. It has to come from somewhere. Okay? It comes either in the form of heat, thermal energy from somewhere else, or work, mechanical energy from somewhere else. Okay? But you can't just create that energy or destroy it. It just isn't going to disappear. Okay? Does it sometimes look like energy disappears? Like, I mean, it's easy to understand. You can't just create it. Stuff doesn't just happen. Okay? But it oftentimes looks like energy does get destroyed. Okay? If you've got a moving car and you slam on the brakes, you take all this mechanical energy and it's just gone because the car stops. Okay? Have you destroyed energy? No. You've turned it into other forms of energy that do not do useful work. You've turned it into sound and heat and light and whatever else. Okay? But it's not destroyed. It's still there. It's just gone to the surroundings as essentially non-conserved energy or wasted energy. All right. So we talked about that flow out. So that's the first law of thermodynamics. Okay, I think that's highlighted in your notes package as well, right? If it isn't, okay, that's just the statement of the first law of thermodynamics. Okay. Okay, how many people have heard of a perpetual motion machine? Okay, what does a perpetual motion machine do? It moves forever. It moves forever without any what? Well, the machine itself would have energy, but what do you never have to do to it? Add any, right. You never have to do any work. A perpetual motion machine, supposedly, would run forever and require no energy to be put into it. Okay? Or you might have to get it started, and then it would just go forever. Okay? Now, if this machine can run forever, what can it never do? Okay, I walked right into that one. I was totally thinking of something else, but you're right, it would never stop. Yes, okay, you're right, it would never stop. What else can it never do? 4-letter word, starts with W. Work. If you could even build a perpetual motion machine, which would be impressive, it would be utterly useless other than as a scientific curiosity, because it could never do any work. The moment it does work, what is it transferring away? Right. And if you never put any energy into it, it transfers energy away to something else, then it's going to what? Stop. Okay? The whole reason a perpetual motion machine can run forever is because it never does any work. Okay? If it does work, it loses energy because work is a transfer of mechanical energy. Or it gets hot and loses energy as heat and stops. A perpetual motion machine has to be perfectly isolated. Okay? It can never exchange anything with its surroundings, especially energy. Because if it did, it would stop. Okay? So that means a perpetual motion machine could never do anything useful. It could just run. Okay? That's all. Just run. And that's all it would do. Okay? Now, what would a perpetual motion machine sound like? Nothing. Exactly. A perpetual motion machine would be silent. Perpetual motion machine made sound, it would stop. Because sound is a form of energy, and if it came from the machine was losing energy in the form of sound, and it's not perfect. Okay? So a perpetual motion machine would make no sound, okay? Would generate no heat, and do nothing. Right? So all these people who get all excited about the making of a perpetual motion machine, it's ridiculous. They're completely useless. Right? They can never do anything. All right. So there were some ideas on what that would look like. Okay? But the second law of thermodynamics forbids the creation of a perpetual motion machine. Okay? Because any conversion of energy results in a flow of energy away. Okay? And the second law of thermodynamics describes the direction of that flow. Okay? Energy always flows from the higher energy object to the lower energy object. Okay? So these were some of the ideas. There was this idea of the pi wheel with the arced sectors. Okay? And the idea was that it would spin forever because the marbles, okay, would roll along here, and when they got to the outer edge, their weight would push that edge down, and when they got to the bottom, because the arc was the other way, they would roll back to the center, and it would be easier for this side to go up, and this side would always be driving, and it's ridiculous. Okay? Because what happens as this goes around and around? It makes sound, yes. The marbles roll along these arced pieces, they're making noise. There's friction there. Okay? Friction is the death of all perpetual motion machines. Okay? There's always going to be energy lost because of friction. You can't perfectly isolate something that way. Okay? I always thought this one had some promise, though. Okay? This one with the magnet. So you put these like metal ball bearings or something like that on here, and they would be drawn up by the magnet. And then they would fall down through the hole and come back to here. The only problem is this has to stop because to open this door requires energy. Okay? I don't know how you get around this. It's a decent idea because a magnet's kind of free, but technically the magnet is always putting what into this system? Energy. So it's not technically a perfect machine then. There is an energy input here, and it's the magnet. All right, so understand second law of thermodynamics, okay? Describes the direction of energy flow in natural processes. It states that thermal energy always flows from a hot object to a cold object, but never naturally from a cold object to a hot object. Never naturally can it be done. Can I make heat energy go from a cold object to a hot object? It won't happen naturally, but can I make it happen? Yes. Your refrigerator does it all the time. In order to keep your food cold, your refrigerator pumps heat from inside the fridge, which is 4 degrees Celsius, into the surroundings, the rest of your house. Ever notice the warm air that comes out from under the bottom of the fridge? Okay? That warm air is the heat energy that the fridge has absorbed from your food. Okay? It is pumping that heat from the cold area to the warm area. It's like active transport, except it's for energy. Okay, we'll leave it at that. Test Monday. You want to start early? You can start early. Okay? You have to be here at, I think, what did I say, 10 after or quarter after? Somewhere in there, 10 after, quarter after, okay? Make sure you're here, okay? And have your writing utensils. That's really about all you need. Okay, so if everybody can wipe down their desks, okay, and mask up.